All right, video number two. So in this kind of series, right, I don't expect to teach you all of linear algebra because one, I don't know all of linear algebra, and two, uh, we're going to take the class anyway, and Harvey Mudd professors are going to be much better than I am. So I mainly just want to give you like a brief introduction and also give you some intuition behind some of the things that aren't normally explained. Like a lot of times you're just going to be given formulas probably because we're not going to have so much time. So in this video, we're going to start with some geometric intuition about what kind of spaces we're working with. The next video will also be kind of related to the same topic. So the first thing we can talk about is what is dimension, right? Like, what does it mean for something to be two-dimensional or three-dimensional? And we kind of have like a general intuition of what that might be. Well, mathematically. And I think the way I think about it is it takes, say if something's n-dimensional, then it takes n being some integer, it takes n parameters to describe where you are in this kind of space. So in one-dimensional space, an example of a one-dimensional space? Well, a line, right? It only takes like one number, right? Say this is a number line. It takes one number to define where you are on this number line, right? It could be 5, it could be -5. But if you suddenly make this a two-dimensional space, you're essentially adding another axis, another degree of freedom. So if you're over here, you're going to need two numbers or two parameters to describe where you are, right? This might be 4, 2. And again, if you add another axis or something and you go up a dimension, you're going to need yet another parameter to describe where you are in the space. So that's kind of the idea of dimension, and that's really important because in linear algebra, like these axes might not be exactly orthogonal to each other. Like you might have axes that are very close to each other, but as we'll come to learn, sometimes if they are different in angle at all, we're going to need more parameters to describe where we are in the space. So we kind of need to expand our idea of what dimension is to be something more general. So with that in mind, let's go into this idea of span. So the idea of span is related to the idea of linear combinations, and these are basically using the operations we talked about last time, which we are constrained to in linear algebra, which is the scalar multiplication of a vector and the addition of two vectors. So these are the only two things we can do, right? Because we're working linearly. We can't do anything super fancy. But just with these two things, we can do a lot. So let's draw a quick two-dimensional plane. This is R2. And let's pick a random vector. Let's just say it's 1, 1. And again, sometimes when I'm drawing vectors, I'm just going to draw the point at the end of the vector, and we're just going to assume that they start from the origin. That way I can draw like a bunch of vectors on here and it won't get too messy. And just remember that they all start from the origin. So I'm going to start doing that right now. We have our 1, 1. Now, when we talk about span, sometimes it'll be written like, what is the span of 1, 1? Well, it's like all of the vectors you can get by using these two combinations. So the first thing we can do is multiply by a scalar. Let's look at what that'll do to our vector. Obviously, if we scale it, it can get really long. So you might get vectors out here. It can, if you multiply by a negative number, it can go over here. If you multiply by a fraction, it'll get really small. And if you took every single possibility, you would get a line, if you can kind of imagine that. Now, the second combination doesn't really come into play because we only have one vector to work with. So what is the span of 1, 1? Well, it's this line. Every possible linear combination of 1, 1 lies on this line. What's the dimension of this line? Well, because it's a line, it's one-dimensional. And you notice there's a kind of relationship here between how many dimensions our span has and how many vectors we're spanning. There is a caveat to that we'll touch on later when we talk about linear independence. But moving on, let's add another vector here, and we'll see what the span of those two vectors are. Now remember, what is span? It's all the possible linear combinations of these two vectors. Linear combinations being any combination using these two properties, either scalar multiplication or addition. So now we have a lot more possibilities. Because basically we can multiply the first vector by a scalar, we can multiply the second vector by a scalar, or we can add the two vectors, or we can add multiples of the two vectors, right? There's a lot more possibilities. In general, right, we can write the possibilities as some constant c times 1, 1. And then we can use addition as well. That's our second property here. And we can go back to using the first one, some constant d times 1, negative 1. And depending on what c and d are, these will be all the possible linear combinations. So let's kind of see what these look like on the graph. Let's first set d equal to 0, just to make things simpler. And you'll notice that just leaves us with the same span that we had before with just 1, 1. So that'll give us this line. But now if we let d vary, let's set c equal to 0 now, and let d vary, well, that's just going to be the span of this 1, negative 1 vector. 1, negative 1 points roughly here. So if we scale it up and scale it down, we'll get this sort of thing. And remember, by drawing this line, I'm drawing an infinite number of vectors that all lie along this direction. Now, forgetting the equal to 0, because c and d can be anything, if we said we had c equal to 1 and d equal to 1, again, just random, well, we'd go 1 up here, and then 1 over, and then 1 over here, and we'd end up somewhere over here, something like that, right? And then again, maybe c is 2 and d is 1, we get here. C is 2, d is negative 1, we get here. If you start thinking about all of the combinations, you know, moving in the direction of 1, 1, and then moving in some multiple of the direction of 1, negative 1, you'll start to realize you can go quite a few places, right? Depending on, you can go here, you can go here, you can go here. And if you really think about it, you can go anywhere in R2. And maybe you want to kind of pause and think about why that might be true. With some constant multiple of 1, 1 and some constant multiple of 1, negative 1, you can go anywhere in R2. And what that means is that these two vectors span all of R2. And again, you might be thinking in the back of your head, is there something to do with the fact that we have two vectors? All right, as I was saying before, my computer ran out of storage, which was tragic. I need to get a better hard drive. But anyway, I was saying maybe there's some relationship here between the fact that we have two vectors that are being spanned and the fact that we spanned a two-dimensional space. And that's mostly the case. Most of the time, if you have two vectors and you take the span of them, then you're going to get a two-dimensional span. If you were in 3 dimensions, you'd get a plane. If you're in the two-dimensional world like we are here, you're going to span the entire two-dimensional space. There is a case where it doesn't happen. Maybe you want to take a sec to think about when taking the span of two vectors would not get you a two-dimensional space. The answer to that is if they're pointing in the same direction. So if instead of 1, negative 1, we made this second vector 2, 2. The key thing to notice here is that 2, 2 is a scalar multiple of 1, 1, and it lies on this original red line that we have. So adding it to the span will not allow you to access other places. By adding it in some linear combination like down here, it won't get you anywhere else. Because what you'll notice is if we just kind of do some algebra, again, there's a geometric way to look at it and an algebraic way. We'll notice that we can factor out a 2 here, and we'll get c times 1, 1 plus 2d times 1, 1. And we do some math here, and we get c plus 2d, which is essentially just a constant, times 1, 1. So we notice that our linear combination of two vectors essentially just simplifies down to the linear combination of one vector, just the span of the first vector, meaning that our span is just going to be that line. Adding that new vector does not increase our span because they point in the same direction. The term for that, for pointing in the same direction, is linear dependence, right? The opposite of linear independence. Linear dependence means that you're pointing in the same direction. Linear independence means that you're pointing in different directions. So if you have the span of two linearly independent vectors, you're going to get a two-dimensional space. And that's true for 3 linearly independent vectors. You're going to get a 3-dimensional space, etc., etc. So this bullet point on spanning the entire dimension, right? That just means whether you're spanning the entire R2 or whether you're just spanning a line in R2, right? That would be a subspace of R2. We'll talk more about the true definition of a vector subspace next video. But so yeah, these are some ways of talking about dimension, talking about space, talking about vectors that will be pretty useful in linear algebra.